Come with me on a journey, not through the vast expanse of space where stars are born and galaxies collide, but through the often overlooked yet profoundly important dimension of sequence. We're talking about the order in which things happen, the flow of information, the very structure of time itself. Our universe is built on sequences, from the smallest atomic vibrations to the grandest cosmic events. Think about it. Words strung together to form sentences, music composed of notes arranged in a specific order, stock prices fluctuating in patterns. Even the very blueprint of life, DNA, is a sequence of genetic code. For years, computers excelled at processing single snapshots, isolated pieces of information, analyzed in a vacuum. They could identify a cat in a photo with remarkable accuracy, or solve a complex static math problem in the blink of an eye. But understanding the flow of events, the dynamic nature of reality, was a different story. The context that comes from order, the relationships between things that happen one after another. That was a significant challenge, a hurdle that seemed difficult to overcome. Enter the Recurrent Neural Network, or RNN, a revolutionary architecture designed to tackle this very problem. RNNs are designed to remember past information, to connect the past with the present, creating a sense of continuity and understanding. This memory lets them grasp the nuances of language, hear and appreciate the complexities of melodies, and even predict, with varying degrees of accuracy, what might happen in the future. Sequence is not just a concept, it's the fundamental language of life itself and the cosmos that surrounds us. To build truly intelligent systems, systems that can interact with the world in a meaningful way, we need them to understand that what happened before inevitably shapes what happens next, the very essence of cause and effect. RNNs provide that essential context, that crucial link between past, present, and future, reading the story hidden within the data, and seeing the intricate connections that unfold through time. So, let's embark on this exciting journey together and explore how these remarkable networks learn, how they remember, and yes, even how they sometimes forget. This is far more than just computer science. It transcends the boundaries of a single discipline. It's about replicating, in code, the fundamental human ability to link yesterday, today, and anticipate tomorrow. The journey into the world of RNNs is, in essence, a journey into understanding sequence itself, the very fabric of our reality. To understand recurrent neural networks, or RNNs, we need to delve into their unique architecture. These networks aren't just another type of neural network, they're specifically designed to handle sequential data. So let's look at their blueprint to understand how they achieve this. We'll break down the components and see how they interact to process information over time. At the core, RNNs are built from simple units, much like any other neural network. These units are the fundamental building blocks that perform computations. These units are organized into layers, creating a structured network that can process complex data. The arrangement of these layers is key to the RNN's functionality. The input layer is where data enters the network. This is the starting point for any sequence we want the RNN to analyze. Data enters one piece at a time, like a word in a sentence, a frame in a video, or a stock price in a time series. This sequential input is what sets RNNs apart. Next is the hidden layer, the engine room of the RNN, where the magic happens. This layer is the heart of the RNN, responsible for processing the input and maintaining a memory of past inputs. Unlike standard feed-forward networks, which process each input independently, the hidden layer in an RNN receives both the current input, the piece of data it's currently looking at, and its own previous state, a memory loop that allows the network to retain information over time. This feedback mechanism, this loop, is what gives RNNs their recurrent nature. It lets the network remember what it's seen before, allowing it to understand context and relationships within the sequence. The hidden layer combines new input with its existing memory, creating a new, updated memory state. This process of combining input and memory, updating its understanding, continues as the sequence unfolds step by step. Then comes the output layer, the final stage where the network presents its findings. This is where the network makes predictions, generates text, or makes decisions based on the processed sequence. The output is the result of blending the present input with echoes of the past, creating a context-aware response. the entire structure from the initial input to the final output. Input, hidden state, output forms a dynamic system specifically designed for processing sequences of information. The crucial loop, the recurrent connection, ensures that a summary of what's been learned is fed back into the network for the next step in the sequence. This loop is the key, the secret ingredient that makes RNNs so powerful for sequence-based tasks. It's this loop that lets RNNs understand sequences, recognize patterns over time, transforming static processors into dynamic learners capable of adapting to the nuances of sequential data. It's how they learn from the temporal patterns that define our universe, from the rhythm of speech to the fluctuations of the stock market. Let's dive into the inner workings of a recurrent neural network, or RNN, and see it in action. We'll explore how these networks process information sequentially, making them particularly well-suited for tasks involving sequences of data. Think of things like understanding sentences, predicting stock prices, or even generating music. We'll use a simple sentence as our example. The cat sat. The RNN processes this sentence one word at a time, meticulously analyzing each element in the sequence. This sequential processing is key to its functionality. You can think of it like watching frames in a movie, where each frame builds upon the previous one to tell a story. At time step 1, the first word, the, enters the input layer of the RNN. This is the initial piece of information the network receives. The hidden layer, the core processing unit of the RNN, then takes this input and processes it. It starts with a blank slate, an empty memory, ready to learn from the incoming data. This initial state represents the network's understanding before it has seen any of the sequence. The hidden layer then creates a hidden state, a mathematical summary or vector representation of the word the. This hidden state captures the essence of the word in a way that the network can understand. At time step 2, the next word, cat, is fed into the input layer. Now, the hidden layer doesn't just process cat in isolation, it combines the information from cat with the memory it has of the, which is stored in the previous hidden state. This combination results in a new, updated hidden state that represents the phrase, the cat. This new state is richer and more informative than the previous one, as it now holds more context about the sequence. At time step 3, the final word, sat, is added to the sequence. Again, the hidden layer doesn't treat SAT as an isolated word. Instead, it merges the information from sat with the existing memory of the cat, which is contained in the current hidden state. This process culminates in the RNN building a complete understanding of the entire sentence, the cat sat. The final hidden state now encapsulates the meaning of the whole sequence. And importantly, at each step along the way, the output layer has the potential to predict the next word in the sequence. For example, after processing the cat, the network might predict that the next word is sat, based on its learned understanding of language patterns. This step-by-step journey, where information is processed and accumulated over time, is precisely how RNNs build a comprehensive understanding of sequences. Each hidden state acts as a carrier, diligently forwarding the context from previous steps to the subsequent ones. This allows the network to effectively make sense of sequences, no matter how long or complex they may be. The entire process is inherently sequential, constantly dynamic, adapting to the incoming information at each time step, and fundamentally context-aware, always considering the preceding information to interpret the present. And that, in a nutshell, is the power and elegance of recurrent neural networks. Let's dive into the hidden state and feedback loop, the RNN's core strengths. The hidden state is the network's memory, a compressed, abstract summary of what's been seen so far. It doesn't store exact words, but captures their essence and context. The network learns what to keep and what to forget, adjusting its memory for the task at hand. This flexibility makes RNNs powerful. The feedback loop is the mechanism that lets memory persist. The output of the hidden layer at one step becomes input for the next. This cycle, process input, update memory, repeat, turns a static network into a dynamic system. Without it, the network would process each input in isolation. The feedback loop lets RNNs build narratives and connect dots across time. It's what separates RNNs from feed-forward networks. How does an RNN learn? Through trial and error, using backpropagation through time or BPTT. BPTT lets errors from the present echo back into the past, helping the network learn from mistakes across the sequence. If the network predicts RAN instead of SAT, BPTT sends the error backward, adjusting connections at each step. The error signal flows from the end of the sequence to the beginning, refining the network's memory. This process is crucial for learning long-range dependencies. For example, connecting France at the start of a sentence to French at the end. BPTT allows error signals to travel back through many time steps. The network learns how early steps contribute to final outcomes. It's computationally intensive, but essential for mastering sequences. BPTT is how RNNs capture relationships woven throughout time. Let's use cosmic analogies to clarify RNNs. The hidden state is like gravity, unseen but shaping everything. A planet's position depends on its past and the pull of its star. An RNN's state depends on previous inputs. The feedback loop is like a binary star system. Each star's movement influences the other in a perpetual dance. The RNN's internal state evolves, history-dependent and dynamic. BPTT is like rewinding a comet's path to find where it went off course. It traces errors backward, adjusting each step to correct the network's learning. These analogies reveal how RNNs process, remember, and learn from sequences. RNNs shine brightest in real-world tasks. In language modeling, they predict your next word when you type. Machine translation uses RNNs to encode a sentence in one language and generate it in another. Speech recognition relies on RNNs to turn audio snippets into text, using memory to understand context. In finance, RNNs analyze stock prices as time series, learning patterns too subtle for humans. They're used in DNA analysis, music composition, and video captioning, anywhere data unfolds over time. RNNs bridge the gap between static data and the dynamic flow of reality. Their memory makes them indispensable for context-aware machines. Whenever sequence matters, RNNs are the tool of choice. RNNs face a major challenge, the vanishing gradient problem. As error signals travel backward through many time steps, they can shrink exponentially, becoming too small to influence learning. This limits the network's memory, making it hard to learn long-range dependencies. The RNN becomes focused on short-term patterns, losing connections across distant events. There's also the exploding gradient, where error signals grow too large, destabilizing learning. Both problems stem from the deep, sequential nature of RNNs. For a time, these issues kept RNNs from realizing their full potential. Learning truly long-term patterns was just out of reach. But new architectures would soon change that. To overcome vanishing gradients, researchers created advanced recurrent units, LSTMs and GRUs. LSTMs add a cell state, a long-term memory conveyor belt, controlled by gates that decide what to keep, forget, or use. These gates are tiny neural networks learning when to open and close. GRUs simplify the process, merging gates and states for efficiency while retaining power. Both architectures protect memory, letting error signals travel back over hundreds of steps. This enables learning of long-range dependencies once impossible for simple RNNs. Today, LSTMs and GRUs are the backbone of complex sequence tasks like translation and speech recognition. They've unlocked the true potential of recurrent processing.